In this video, we'll be talking about our 1 kilogram load cell sensor. I'm Calvin Shaw.
I'm Kyle Sheritz.
Yeah, I'm Zach Tieford.
The objective of this project was to build a measurement system to ideally measure the weight of produce in a market. We aim to investigate the static and dynamic capabilities of our sensor. The load cell works on the principles of a cantilevered beam. When a mass is placed on the end, a bending moment is put on the beam. This causes tension on the top and compression on the bottom. With a strain gauge mounted on top and bottom, a change in resistance occurs and a voltage output is given. The load cell is powered by a 5-volt power supply, which passes through a tuning potentiometer acting as a voltage divider. From there, the signal is put into a op-amp, which amplifies the signal and outputs the signal to the DAC.
This is the physical system represented by the circuit on the previous slide. We used a digital 10 Hz low-pass filter with our DAC to cut out the noise. On the right, you can see our method of hanging the masses from the 1 kilogram load cell. For the static calibration, we first took a voltage reading with no load applied, and then starting at 100 grams, we took a voltage measurement reading every 50 grams up to 1 kilogram. And then starting at 1 kilogram, we measured the voltage while unloading, taking off 50 grams every reading down to 100 grams, and then took another voltage reading with no load applied. For the dynamic calibration, we began to record data with no load applied, and then we dropped a 1 kilogram load a very short distance onto the load cell hook, and this was done so that there wasn't any bouncing of the mass to skew the results. And this was done a total of 3 times. Our design stage uncertainty consisted of 4 major parts. For the hysteresis error, first we did a polyfit of the data as we added 50 grams, and then the data as we took away 50 grams, and we fit those with third-order polynomials, and then we found the max difference between those curves. For the linearity error, we created a curve of all the average values of when we added 50 grams and when we took away 50 grams. We created a linear fit to that, and then we found the max difference between those two. The mass error was actually given in the data sheet. To find the quantization error, we used the full scale range given in the DAC datasheet, and we calculated the resolution given the number of bits also from that datasheet, and then the quantization error was calculated to be plus or minus 1/2 of that resolution.
In the figure shown is our static calibration raw data. In the blue, you can see the data from the upsweep, and in the orange, you can see the data from the downsweep. To analyze our static calibration data, we then curve fitted a third-order polynomial through the upsweep and through the downsweep data. We also curve fitted a linearized line through the average of upsweep and the downsweep data. From these results, we were able to get our hysteresis, linearity, mass, and quantization error. From all these errors, we were able to find our overall design stage uncertainty. These are our dynamic calibration results, which once again, we just dropped a 1 kilogram weight onto the load cell and got the step response. To analyze our dynamic calibration data, we took an average Y0 and Y infinity from the raw data. We then plugged these values into the equation shown on the slide to get the z-plot shown on the left. We then fit a linearized line through the linear region of the z-plot, and the slope of that line is equal to -1/tau. This is how a tau value of 0.0237 seconds was calculated. The 3 key parameters calculated from this 1 kilogram load cell sensor were static sensitivity, design stage uncertainty, and time constant. The static sensitivity was about 53 grams per millivolt, the design stage uncertainty was about 297 grams, and the time constant was about 0.02 seconds. Thank you.